Good day, good day, good day, everyone. Welcome again to this another installment of Rate of Reactions. If you haven't watched the previous video, please start there. Start with that one so that you can be able to catch on what we've already covered. So what I want to do today is I want to just make sure that I just give you just a bit of variety when it comes to the type of questions that you can expect on the section of rates of reactions. So if you haven't subscribed, please make sure that you subscribe and hit that bell button, okay, so that you get notifications every time I post a new video. All right, so without any further ado, I'm just going to do past exam questions. As I said, if you haven't watched the first video, please make sure that you can you do that before you watch this one. And then if you need to get in touch with me, I can be found on my email address. That's mlungisi.m.nkosi@gmail.com. That's my name, MLUNGISI.M for Mary .nkosi@gmail.com. If you have any questions, please just throw them in there. Otherwise, just hoy a comment. Okay, right, let's get into it. So as a start, I want us to start with it's a past paper. Okay, I took it from the senior certificate exam question, and in this case I just want us to do the question on rates of reactions, right? So if you don't mind, we're going to start with that because we didn't cover a certain section or certain type of questions yesterday. Right, now let's begin. Okay, so they give us this question. All right, so please, it's from 2019. Okay, so they say learners use the reaction of sodium thiosulfate solution with dilute hydrochloric acid to investigate several factors that affect the rate of a chemical reaction. The balanced equation is given, so there they give you that balanced equation there. Okay, so there are those factors. There's the equation and the statement, and of course they start with the definition. They want us to define reaction rate. We did say it's the change in the amount of products formed per unit of time, or we can say it's the change in the amount of reactants used, right, per unit of time. Right, now let's get into the gist of the question. So now they have 3 investigations. So that's investigation 1, 2, and 3. Please, if you can, just download this paper for yourself so that you can be able to follow. Okay, right, now they say they've got 3 investigations. Okay, they say the results obtained in investigation 1 are in the graph below. So this is the graph of reaction rate versus the concentration of sodium thiosulfate. Now look at this. So the reaction rate increases when you increase the concentration. We did say that yesterday, right? That if you increase concentration, what it does is that obviously you get more moles per unit volume, and in that case there are more collisions per second, and as a result that is what increases the rate of reaction. By the way, remember we did say that we've got 5 factors that affect reaction rate. Can you just try to remind yourself? We said it's concentration, it's temperature, it's pressure, it's surface area, or you can say state of division, right? That's for solids. And in this the last one is a catalyst, right? The use of a suitable catalyst. All right, now obviously here they're investigating the factor called concentration. All right, and we're saying obviously as we increase concentration going that way, what it does is that the reaction rate increases. Right, now they say for this investigation, write down the dependent variable. You remember what I said to you yesterday, ladies and gents? Right, so this time they represented it in the form of a graph, right? So the dependent variable will be found usually on a graph. It's always on the y-axis, right? So in this case, your dependent variable is reaction rate. And for those who watch the video that we posted on reaction rate, you'll notice that I always said reaction rate is always your dependent variable, right? And which one would be your independent in this case? It definitely would be concentration, right? So as you change concentration, it affects the reaction rate. Okay, right. And then they say write down the conclusion that can be drawn from the results. Okay, that's exactly what I just said. Okay, right? That an increase in concentration, okay, increases the rate of reaction. That's what we can conclude, isn't it? Right? An increase in concentration will definitely increase that reaction rate. So that obviously they didn't ask for an explanation of what exactly causes that, but you can include that if they did ask you. Okay, right, now let's go on to the next part. Right, so now they give us the next question. Okay, the next set of questions based on the same investigation. Okay, now they say to us, okay, so there it is. I'm just gonna bring it closer to the camera. They said the Maxwell-Boltzmann distribution curve A and B below represent the number of particles against kinetic energy for the reaction at two different temperatures. Now, if you watch the previous video, you remember I said when you increase temperature, what it does is that it widens the distribution, and what it does is that it lowers that peak, isn't it? So it means that oh, and by the way, the third thing that it does is that it shifts that average. Okay, so you have an increased average, you've got a widened distribution, and you also have a lowered peak. So when I'm looking at those two graphs, it means that the graph B is a graph that has a higher temperature than that of graph A. All right, and then P there, okay, I'm sure they're going to ask us about that. P represents what we call the activation energy. Remember, we said that's the minimum energy required in order for effective collisions to take place, or in this case for a reaction to take place, right? So it means at point P, anything above, or if particles have got energy that is above P, it means that these will be able to undergo what you call effective collisions. It means they will be able to form products. Okay. And then now they say, what does line P represent? Okay, that's exactly what we said. It represents activation energy. Okay, look at this. They shown you what the shaded part represents. They said particles that undergo effective collisions, right? Of course, they can only do that if they have a higher, they have energy that is higher than the activation energy, the minimum energy that is required, right? Okay, so 5.3.2, they say which curve A or B was obtained at a higher temperature? Definitely that would be curve B, right? And then they say explain in terms of the collision theory how an increase in temperature influences the rate of reaction, right? So we said an increase in temperature. Remember what happens when we increase temperature? When we increase temperature, it means that the particles now have got a greater average kinetic energy, isn't it? So they are able to move faster. So greater kinetic energy, average kinetic energy, right? It means that there's more particles that have energy that is greater than the activation energy, right? So just to put it in simple terms, it means that if I increase in temperature, would increase the number of particles, or rather would increase the average kinetic energy, right? Now more particles have sufficient kinetic energy, or a kinetic energy greater than the activation energy, and therefore that will increase the rate of the reaction. Okay, so obviously there'll be more collisions per second in that case, and therefore more effective collisions rather per second, and as a result we increase the rate of the reaction. Okay, and then 5.4. all right, I hope you are still with me. I'm not going too fast on that one. If you want to, you can play that back. Okay, right. Or maybe let me just mention that again in much more clearly. right? We said an increase in temperature, right? It means that, an increase in temperature will increase the average kinetic energy of the particles, right? Now, more particles possess sufficient kinetic energy, right? And that will increase the number of effective collisions per second. Okay, I hope that is a bit more clearer. Right, so 5.4, right? Now they say to us the potential energy diagram X and Y below represents the reaction under the under two different conditions. Now, if you remember, we went through this graph again in the previous video on reaction rate. So graph X would be the one probably without the use of a catalyst. And we said when we use a positive catalyst, what it does is that it lowers that peak there, right? So in this case, it simply means that graph Y was obtained when we have a suitable catalyst that is used. Okay, right, now let's go through the last question. They say in one of the investigations, 100 cubic centimeters of 0.2 moles per cubic decimeters of hydrochloric acid, so there it is there, right, reacts with excess sodium thiosulfate, and the solution is then filtered. All right, so after filtration of the solution, 0.18 grams of sulfur is obtained. Calculate the percentage yield. So I'm going to go through this question with you. All right, so what I want to do first is let me just go back and rewrite that formula for myself, right? So we're going to do that together, right? So what did we have? We had sodium thiosulfate, so there it is, 2S2O3, right, plus 2HCl, and what it does give us is 2 moles of sodium chloride, okay, plus SO2 plus sulfur, which is in a solid state, plus H2O. Now, very important for us to obtain that reaction first. Why is that? Because what it does is that it will give us the ratios in terms of their stoichiometric ratios, that is. So now let's look at the information that is given. Now, remember they told us that we've got 100 cubic centimeters of a 0.2 mole per cubic decimeters of what? Hydrochloric acid. So let me write that information down. So I've got the concentration. Okay, so concentration of hydrochloric acid is 0.2 moles per cubic decimeters. Okay, and they also gave me the volume of the acid to be 100 cubic centimeters. Okay, right, and then what they do tell me is that so they react, they say after filtration, right? Now please, before we get to the filtration part, they say reacts with excess sodium thiosulfate. What does that mean? It means if this reaction is going to stop, it's not going to be because we've run out of sodium thiosulfate. It means that hydrochloric acid is the limiting reagent. It's the one that is going to limit the extent of the reaction. So in a sense, what that tells us is that we can only make as much products as the hydrochloric acid allows us to. Okay, so it's the one that's going to limit the amount of sulfur, for instance, because they've asked us about sulfur, that we make. However, what we're going to do is we're going to compare, because they want us to get the percentage yield. Let's find out what the theoretical yield is. That is, how much sulfur am I supposed to produce if theoretically I am able to use up all of the hydrochloric acid, right? So now I'm going to simply say, right, so for this one, okay, if you look at it, So is it possible for me to get the number of moles of hydrochloric acid? Yes, it is. So the number of moles of hydrochloric acid, okay, so this comes from the concentration. They give me concentration and volume. So the formula starts with concentration is number of moles over volume, right? So my concentration is 0.2. So I'm substituting there first. Okay, I want the number of moles and I'm given the volume. It's 100 cubic centimeters. Please remember, when I use this formula, you're supposed to use that in cubic decimeters. So you divide that by 1,000. So if I'm supposed to get that in cubic decimeters, all I do is divide that by 1,000 and it gives me 0.1 cubic decimeters. Okay, so I get 0.1 there. Okay, so now if you cross multiply, so number of moles is going to be 0.1 times 0.2. That will give me 0.02 moles. Now remember, what are these? The moles of hydrochloric acid. Okay, right. Now I have the number of moles of hydrochloric acid, and remember that hydrochloric acid is the one that is going to limit the extent or the amount of sulfur that is going to be produced, right? Now, theoretically, right, if I use up all of these amount of moles, theoretically, how many moles of sulfur can I have? Now look at this. I'm going to do this with you, right? The formula says for every 2 moles of hydrochloric acid that I use, I get 1 mole of sulfur. Can you see that? That's what my formula tells me. It tells me for every 2 that I use of this one, I get 1 of that, right? So now I want to find out if I use 0.02 moles of hydrochloric acid, right? So notice it's on the same side, right? If I use 0.02, which is those moles there, right? My question is, how many moles of sulfur will I produce? Okay, right, so I'm using that as n. How many moles? So if for every 2 I get 1, if I use 0.02, how many moles am I going to get? And you guessed it, it's going to be 0.01. You can cross multiply. By the way, how I like doing it is that this actually works quite well. If you do that, you start at your formula, right? Say for every 2 there's 1. For 0.02 of this, how many of that am I going to get? And then you cross multiply. But you just cross multiply just the coefficients, right? So I'm going to say n multiplied by 2. That will give me 2n, right? 0.02, which is equals to 0.02 times 1 will give me 0.02. And if I divide both sides by 2, I get n is equals to 0.01 moles. So theoretically, ladies and gents, it means that the number of moles of sulfur, okay, that I'm going to produce, okay, theoretically, are supposed to be 0.01 moles. Now I want to know if this is the number that I'm supposed to produce. Let's convert that in terms of mass. And why do I want to do that? Because I want to compare apples with apples. I want to compare mass with mass. Because remember, in my question, they had given me the mass as a yield, that given me the mass of sulfur, 0.18 grams there, the actual yield, right? So now, how am I going to get that theoretical yield? Now I've got the number of moles of sulfur. So I know that number of moles, that's mass divided by molar mass. Number of moles is 0.01. Okay, I want the mass, and the molar mass of sulfur is 32, right? I'm going to just continue over the other side there. Sorry about that. Okay, right, I'm going to continue over to this side. So now I want to find out what the mass of it is, right? So I get a mass of 3.2 grams. So theoretically, if I used up all of that hydrochloric acid, I am in turn supposed to get 3.2 grams of sulfur. So what is this? This is the theoretical yield that I'm supposed to get, right? So now, what was the actual yield of sulfur? Oh, sorry, I think I just made an error there. Okay, so this is 0.32 grams. Okay, 32 multiplied by that, it will give us 0.32. Okay, let me just verify that. Okay, so 0.01 times 32, and okay, right, that's exactly what you get, 0.32. So that's 0.32 grams, right? Now I am going to say, right, we want to calculate the percentage yield. Okay, right, how do we get the percentage yield? We say, well, the percentage yield, it's going to be the mass. Okay, so it's going to be the theoretical yield, the actual yield, right? So it's going to be the mass actual, the one that we found, right? And we divide that by the mass theoretical. Okay, and we multiply that by 100 to get the percentage, right? So what was my actual mass? Okay, the actual mass is what they told us. They told us we got 0.18 grams. So that's 0.18 divided by, what's my theoretical yield? Theoretically, I was supposed to obtain 0.32. Okay, so that will give us the percentage. Okay, so you can do that. That's 0.18 divided by 0.32. Okay, and we multiply that by 100. Okay, right, and I get an answer of 56.25%. Okay, right, you can verify that for yourself. Okay, I hope that you understood that question. It was out of 6 marks, quite a sizable question, and I hope that it made sense to you. Right, so what I want us to do is to tackle another question. All right, and it's the last one that I'm going to be doing. I just want to do 2 questions with you, and then we take it from there. Good? All right, fantastic. All right, so we take our second question. Okay, source this one from the Eastern Cape. That's September 2019. That was a prelim paper. Okay, so they say to us, a group of learners, use the reaction between magnesium and hydrochloric acid to measure the average rate at which hydrogen gas is produced. They add 10 cubic centimeters of a 1 mole per cubic decimeter of hydrochloric HCl to 0.048 grams of magnesium powder, okay, in an Erlenmeyer flask. Okay, so they give us the balanced equation. So first of all, so let's look at what they want from the question. So they give us a graph there, okay, and you can see the graph shows us the volume of hydrogen gas that is produced. Remember, this reaction produces hydrogen gas, right? So as a result, so you can see it starts from 0, and the hydrogen gas increases because you are producing more and more and more of it until obviously we get to this point at 120 seconds, right? This is when the reaction reaches completion. Why? Because you've actually run out of one of your reactants, okay? One or both of them, right? So we're going to look at it. Now you must just keep in mind that there could be a reactant which is said to be a limiting reagent, right? So we're going to look at that as we go along with the question, okay? Right, now they say, first of all, define reaction rate. I'm sure you've got that by now. You can sing it, you can rap it, you can hum it. Yeah, you can do everything with the definition there. Right, so they say calculate the volume of hydrogen gas produced in the first minute if the average rate of production of hydrogen gas is 0.67, look at the units. The units there are given in cubic centimeters per second. So it means when you take the rate of reaction, remember it's the change in amounts. Okay, so amounts could be cubic centimeters, it could be moles, it could be mass in grams, right? So all you need to do is just check what the units are so that you know what to use. So obviously here it's going to be volume divided by time, right? So in this case we're going to have, okay, in our first question, so we know that the rate of reaction, so rate, okay, okay, I don't know if I need to make an adjustment there. So rate is equals to the change in volume this time divided by the change in time. Please don't confuse that for change in velocity, right? So that's change in volume divided by change in time, right? So they have given us the rate of the reaction. So if you notice there, so we're going to say, okay, they said for the first minute, right? So 1 minute, that would be 60 seconds. So that would be between this point here and 0, right? So let's look at our graph. So the change in volume, I'm going to say, rather let me say volume final minus volume initial divided by time final minus time initial, right? So we were given the reaction rate. They said it's 0.67. And note, my volume needs to be maintained in cubic centimeters because my rate is actually in cubic centimeters, right? So what is my volume final? Okay, right, I don't know what that volume is, but remember that's what they are looking for, isn't it? So V final, okay, so that volume at 1 minute minus what's my initial? I started at 0 divided by time final. That volume final happened at the 60th second, right? And obviously when the volume was 0, also the time was 0 on our graph, right? Okay, so all we're going to do, and remember this is equals to 0.67. Okay, I can say over 1 so that I can make it easier for me to solve mathematically. Right, so we can just cross multiply. VF minus 0 is VF. Okay, VF times 1, that is going to be VF. So 0.67 times 60. Okay, I get a value of 40.2. Okay, so I get a value of 40.2, and so it means that our final volume in cubic centimeters was 40.2 there. Okay, right, so that's our first question. And then or rather second question, that's 5.2. Okay, and then they say to us how long in seconds, okay, does the reaction take to run to completion? Okay, give a reason for the answer by referring to the gradient of the graph. Okay, so look at this. When does it reach completion, or when do we get to that completion point? So that's at 120 seconds. Can you see? And why is that? Because the gradient of the graph becomes 0. Okay, so that would be our answer there. Right, and then the next question, I'm sure most of you would now be shivering if you see this, that it's 7 marks. But don't worry about it. We'll take it one step at a time. Right, so now they say to us, okay, see, so they say calculate the mass of the reactant left in the flask, right, when the reaction is complete. Now, first of all, we need to find out, okay, which reactant rather is left after after we have reached completion, right? So we need to check first which one is the limiting reagent, right? Okay, and so as a result, which one would therefore be our the one in excess. Okay, so we need to check which one would be our limiting reagent and which one would be in excess. Okay, so we need to check what we are given, right? So I'm just going to rewrite that reaction again so that I can try to show what we have there. So we've got magnesium. So we've got magnesium that reacts with 2 moles of hydrochloric acid. Okay, and that gives us magnesium chloride plus hydrogen gas. Okay, so that's gas, that's aqueous, that is aqueous, and that is a solid. Okay, right, now what I'm simply going to do is the following. Let's write down the information that we have for each. So they gave me the volume of hydrochloric acid. Okay, so the volume is 10 cubic centimeters. 10 centimeters cubed. And then they also gave me the concentration to be 1 mole per cubic decimeters. Okay, all right, so that's what we have there for hydrochloric acid. And then magnesium, they had given me the mass 0.048 grams. Okay, so you know what, because I wasn't told which one is the limiting reagent in this case, or which one is the limiting reactant, I would need to find that out for myself. Okay, so let's do this. Let's calculate the number of moles of magnesium, right? So let's say this is the number of moles for Mg, right? So this is mass divided by molar mass, right? Because I'm given the mass there. Okay, let me just get my periodic table quickly, right, so that you can see that. So then you head over to your periodic table to get the molar mass of magnesium, and that molar mass is 24. I think you still remember that, no? So we're going to say 0.048 divided by 24. Okay, okay, so that's 0.048 divided by 24. Okay, and we get a value of 0.02. Okay, so the number of moles that are available for magnesium, 0.002 moles, right? And then let's find out what's the number of moles of hydrochloric acid that are available. We're not saying all of them are going to react. Okay, so we just want to find out the ones that are available. So I'm going to say, all right, let's find out number of moles for HCl, right? I've got the concentration, I've got the volume, so I'm going to say it's concentration times volume. But please remember, concentration, they said it's 1, okay, multiplied by the volume. In this case, our volume was given in cubic centimeters. We are supposed to have that in cubic decimeters, right? So we divide that by 1,000. So 10 divided by 1,000, right? So that should give us 0.01. Okay, 0.01, and obviously 0.01 moles. Okay, right. I think if I look at it by inspection, okay, without necessarily having to look at it much, look at this. For every 1 mole of magnesium, you need 2 moles of hydrochloric acid, right? So if you would have those number of moles of magnesium, 0.02, you'd need twice the amount of hydrochloric acid. So that would be 0.04 that you'd need, right? 0.004 that you need. Okay, and in a sense, when you look at this number compared to that, this is a much smaller number, actually more than 10 times smaller, right, than this one. So in this case, it does actually tell me that magnesium would be my limiting reagent, right? So it means that magnesium in this particular case, you can try it out in another way, right? But magnesium in this particular case would be the one that limits the extent of the reaction. It means the amount of hydrogen that I can produce depends on the amount of magnesium that I have. That when the reaction reaches completion, when it stops there, it's stopping because I've actually run out of magnesium, right? So actually, let me use magnesium to find out the mass of the reactant that is left, right? Now, please, I want you to follow me very carefully. Listen carefully. So what did I find? I found the number of moles of magnesium, all right? And I found out the number of moles of the excess amount of, I found the number of moles of hydrochloric acid. And I know that hydrochloric acid, well, I can see it's more than 10 times what more than 10 times what I have of the magnesium, right? So now, I want to say, okay, so these are the number of moles that are available, but how many moles of hydrochloric acid are actually going to react with the magnesium? So now I go to my stoichiometric coefficients. Then I say, well, for every 1 mole of magnesium, according to that reaction, right, for every 1 mole of magnesium, I will actually use 2 moles of hydrochloric acid, okay? Right, please remember, you can't do that with mass. You can only do that with moles, right? So for every 1 mole of magnesium, I will use 2 moles of hydrochloric acid. Now the question is, if I use 0.002 moles of magnesium, how many moles of hydrochloric acid am I going to use? Now notice, when I use this ratio and proportion, I always just simply use the number of moles and not necessarily I use the number of moles and not the mass, right? So I start from my reaction, right? And in this case, I go to the actual things that to the actual numbers or to the actual amounts that I actually have, right? So for everyone, there's 2. So for 0.02, notice the same things on the same side, right? So this is magnesium. I've got 0.02 of magnesium, and I've got an unknown amount of hydrochloric acid. I want to know how much hydrochloric acid will react. So let's cross multiply, right? Remember I said to you, we only use the coefficients, right? N times 1. So the number of moles of hydrochloric acid, N times 1 is N. And in this case, 0.002 times 2 will give me 0.004 moles. Okay, so these are the actual number of moles of hydrochloric acid that are going to react. Are you with me? Right. So it means if I use that amount of magnesium, these amount of moles of hydrochloric acid will actually react. Now, what does that say to us? It says there's an amount of hydrochloric acid that will remain unused, right? Unreacted. So there'll be an amount that is in excess, okay? So I want to find out how much will be in excess. And remember, they said they wanted the mass, right? So let's find out the number of moles of magnesium, of hydrochloric acid that is in excess. So remember, this is HCl, right? So what will it be? It will be the number of moles that we have originally, or you can say the total number of moles that we have, that were given, okay, minus the number of moles that you actually used during the reaction, okay? So in this case, I've got 0.01 minus 0.004, right? Okay, so we will have 0.004. Okay, so we should have 0.006 moles that are in excess. So the amount of hydrochloric acid that is in excess in moles, right, will be 0.06 moles, right? So now can I find out what the mass of it is? Yes, I can, right? I've got number of moles. I want the mass. So you are quite correct. I can say number of moles, that's mass, divided by molar mass. Okay, I've got 0.006. I want the mass. What's the molar mass of hydrochloric acid, right? You guessed it quite right. You're going to your periodic table again. So we're going to say, okay, the mass, the molar mass rather, H is 1. That's that's hydrogen. And chlorine there is 35.5. So it's 1 plus 35.5, which is 36.5. Okay, right? So in this case, we're going to say 0.06 cross multiply there, okay, times 36.5 times 36.5, and we get 0.2. So the mass of hydrochloric acid that you have that is unreacted is 0.219 grams. Okay, so this will be the amount that I have that remains unreacted. So that's how we'll tackle that question. Okay, I would have wished that the examiner would have been at least more it would have gone a little bit easier on us by telling us which one is in excess. I think it would have made a lot of difference. Okay, and in that case it would have saved us from having to find out which of that just having to find out which one is the limiting reagent, right? Right, now let's continue as we are about to bring this to a close. Right, so they say when the concentration of hydrochloric acid is increased, the learners observe that the rate of reaction increases, right? Use the collision theory to explain this observation. Okay, so we know that concentration obviously increases the rate of reaction. Remember, we said, all right, an increase in concentration, okay, will increase the number, okay, of moles, the number of moles that are available to react, okay? So what happens? It means that there'll be more collisions per second, isn't it? So, and that will increase the number of effective collisions. So in this case, there'll be more moles per unit volume, right? So when I increase the number of moles, there are more moles per unit volume. There's more frequent collisions, right? In this case, what it does is that it increases the rate of reaction because there are more frequent collisions per second, right? Okay, so obviously you'll put it nicely. And then the last part, they say in another experiment of magnesium powder, or rather in another experiment, the magnesium powder is replaced with an equal amount of zinc powder, okay? They say redraw the graph provided above in your answer book and sketch on the same set of axes the graph that would be obtained when zinc powder is used. Okay, so what they are simply saying to us is that instead of using magnesium, they are now going to use zinc powder, and they want to know what type of reaction you would get there. Okay, now because zinc reacts more slowly in an acid medium than hydrochloric acid, so obviously it means that the rate of the reaction with zinc would actually be slower than the one where you use magnesium. So let me just show you what the difference would be. So if for argument's sake this is our graph that shows us the reaction between magnesium, okay, so if this is our graph that shows us the production of hydrogen between magnesium and hydrochloric acid. Now when you put zinc, because zinc actually reacts much more slower, your graph would tend to have a lesser gradient, Okay, if it's the same amount, hopefully the same amount of moles or whatever the case may be, right, you still would reach completion. Okay, but the difference would be that the amount of the time that it takes for you to reach completion would be much longer for the graph of zinc than the one where you are using magnesium. Okay, so obviously that's because of the type of material that you use in this case. Okay, right, and I think that will be the last question that I want to tackle. Ladies and gents, once again, I just thought I'd just add these two questions, all right, just to supplement on what we had done previously on rates of reactions. Please, if you have more questions or if you've got things that you still want me to clarify on rates of reactions, you're more than welcome to send those questions through, and then obviously we'll try and tackle those questions. All right, and please, ladies and gents, work hard, study hard, always make sure that you do your best, you give your best, and I promise you the results will come. Otherwise, from me, I'll see you on our next lesson. Okay, thank you so much. Please don't forget to subscribe, and please tell others about the channel so that more people can benefit. Okay, otherwise, thank you. See you next time. Sharp sharp.